Welcome back to the deep dive. When we talk about the future of mobility, the conversation almost always orbits around the premium high-tech stuff.
Right, you hear about autonomous capabilities,
Yeah,
800-volt charging, software-defined vehicles, the whole computer on wheels idea.
exactly. But there is this massive parallel universe in the global auto industry that's quietly and very aggressively redefining urban transportation.
And that's the micro low-speed electric vehicle, or LSEV market.
It's a huge space.
It really is the true revolution of mobility, I think, precisely because it has completely inverted the engineering philosophy.
What do you mean by inverted?
Well, instead of performance stacking and adding more and more features, it focuses on extreme cost efficiency. You're trying to achieve, say, 90% of a car's utility at maybe 10% of the cost.
And today we're not just looking at market trends or some glossy consumer brochures.
No. We are diving into the actual technical bedrock and engineering requirements specification, and SOR, that was developed by a global engineering consultancy for an OEM. This document, it lays out the complete blueprint.
The whole thing.
Everything you need to build a globally competitive micro-EV platform from the ground up.
Okay, let's unpack that. We are, in a sense, stepping into the role of a chief systems engineer.
That's the mindset, yeah.
And your job is to solve this nearly impossible multidimensional puzzle. Design a globally compliant functional EV that retails for less than a high-end laptop, let alone a car.
And the entire philosophy driving this document, this SOR, is a concept called frugal engineering.
Right. For our listeners who might not be familiar with that term in an automotive context, what does frugal engineering actually demand when, the stakes are global compliance and just bottom line survival?
Frugal engineering demands maximum value creation under the most severe constraints you can imagine. It's not just about making things cheaper.
Okay.
It's about achieving the necessary functionality. And this is critical, meeting strict regulatory compliance through strategic elimination.
So it's about what you take out, not what you put in.
Precisely. As a chief systems engineer, your mandate is to cut complexity and cost before you even get to the manufacturing phase. The SOR's core mission here isn't just to design a product. It's to establish a complete system development and integration capability for a greenfield engineering team. You're starting completely from scratch.
Yeah.
So that means you have to design the product and the process at the same time, all while keeping tooling and development costs at an absolute minimum.
That is an immense mandate. You're building the team, the manufacturing process, and the car all at once.
It's a huge challenge.
Our sources lay out 4 strategic engineering pillars that govern every single decision in this spec. It feels like we need to understand these because they're the non-negotiables.
Absolutely. When you approach a greenfield project with this kind of aggressive cost target, and that target means you're competing directly with giants in China who have massive scale, every single technical spec has to trace back to these 4 pillars.
Okay, so what's pillar number 1?
First is regulatory harmonization. The market is, fragmented globally, but you just can't afford multiple distinct vehicle platforms.
Sure, it's expensive.
Way too expensive. So the goal is to create a superset specification. This means you identify the single most stringent requirement across all your target regions, EU, China, US, Japan. You design the core platform to meet that one top-tier constraint.
Can you give us an example?
Yeah, a perfect one is the battery. If China mandates a no fire, no explosion rule after a thermal runaway event, that constraint immediately becomes a global design feature, even if other markets have looser standards.
Yeah.
This minimizes your homologation costs, and it maximizes your market reach. You design once for the toughest rule.
That makes a lot of sense. You let the strictest rule set the foundation for everyone else. It's a smart way to manage that global complexity up front.
Precisely. Now, the second pillar is the absolute immovable anchor, both financially and technically.
Okay.
Extreme cost weight optimization. The target curb weight, and this is excluding the battery, must be strictly under 450 kilograms.
450.
That's not an arbitrary number. It is explicitly tied to meeting the EU L70E passenger vehicle limits. This is the key strategic decision of the entire project.
And why is 450 kilos so crucial? Is it just about efficiency?
No, it's about regulatory arbitrage. It's about finding the necessary safety harbor.
Okay.
Staying below that 450 kilogram threshold legally classifies the vehicle as an L70 heavy quadricycle under EU regulations rather than a full M1 passenger car.
And that classification gives you what?
Access to dramatically relaxed passive crash standards. You avoid mandatory full frontal offset tests, side pull impacts, roof crush tests. If we cross that 450-kilogram line, we would instantly add tens of millions in development costs.
And kill the project.
It would collapse the economic model entirely.
Yeah.
The weight limit dictates the structure, the materials, and ultimately the profitability.
So the engineering decision is purely derived from a legislative definition. That's fascinating. What about production and parts?
That leads directly to the third pillar, BOM efficiency and symmetry. We have to achieve a bill of materials, a BOM test, that lets us compete with the willing mini EV, which starts at, what, $4,000 or $5,000?
An incredible price point.
It's brutal. So this is achieved through mandated engineering techniques. The SOR actually mandates symmetrical design, which was really popularized by the Citroën Ami.
Where the molds for, say, the left and right doors or the front and rear bumpers are identical.
Exactly. This is pure industrial efficiency. It cuts your large exterior panel tooling costs, your CapEx, by 50%, and it radically simplifies your inventory management. Plus, you maximize the use of commercial off-the-shelf components, CO2 cost parts, to avoid high engineering costs.
And pillar 4 is safety. Since we're operating under 450 kilos, we know the vehicle can't rely on mass or big crumple zones. So how does the spec handle occupant protection?
The fourth pillar is safety-first powertrain and active safety. Passive safety protection in a crash is inherently limited by the vehicle's size. So the focus shifts dramatically. You prioritize active safety features that prevent the crash from happening in the first place.
Like what?
Mandatory systems like a pedal misuse suppression system and rigorous adherence to battery safety standards, especially thermal stability. This foundational shift from reacting to a crash to proactively preventing it is really the only viable safety strategy for a lightweight microcar.
That strategic approach gives us the framework. Let's start with that regulatory maze, because it sounds like in the LSEV world, the regulation is the core design specification.
It absolutely is.
And the sources point to Europe's quadricycle classification as the key loophole, the safety harbor you mentioned.
It is the foundation upon which the entire global architecture is built. EU Regulation 198/2013 is the key document. It classifies these vehicles as quadricycles, which lets them bypass the really stringent M1 passenger car requirements. Historically, this was for lightweight motorcycles and utility vehicles, but manufacturers successfully lobbied to expand it to include enclosed passenger vehicles because they saw the massive cost savings.
We need to understand the distinction between the two main classes, L6E and L7E, because it sounds like it completely changes the engineering scope.
It does indeed. The L6E, or light quadricycle, is the true ultra-low-cost path. The definitions are really strict. Max speed is capped at 45 kilometers an hour, max power at 6 kilowatts, and a very low curb weight of 425 kilos.
That's the Citroën Ami's domain. So what's the biggest engineering impact of staying strictly in that L6E category?
The ability to run on a 48-volt low-voltage architecture. This is a massive win for frugal engineering.
Why is that so important?
Because the system voltage stays safely below 60 volts DC. That means you completely bypass the need for costly high-voltage protection and isolation standards.
Okay, so no special connectors.
No requirement for a high-voltage interlock loop, no expensive shielded cables. Connectors are simpler and cheaper. We estimate the savings on the electrical harness and system management alone are easily over $500 per vehicle compared to a higher voltage system. And certification is way simpler.
But the SOR's core target is the L7E, the heavy quadricycle. And this demands a jump in capability and complexity.
The L7E classification allows for a much more practical vehicle, one that can actually integrate into suburban traffic. There's no strict speed limit, but the design goal is set at 90 kilometers per hour.
And the power.
Maximum continuous rated power is capped at 15 kilowatts. And critically, the passenger vehicle curb weight limit is 450 kilograms, which is why that number is so sacred to this SR.
This is where we need to dive into the physics. Why does the requirement to hit 90 kilometers an hour with 15 kilowatts of power force and upgrade beyond a simple 48-volt system? I mean, why can't we just use a 48-volt system with more current?
It's the law of thermal loss, specifically I²R loss, power is voltage times current.
Right.
To deliver 15 kilowatts of power continuously at 48 volts, you'd be pulling roughly 312 amps.
That's a lot.
It's a huge amount of current. Now, consider that running through a cable. The heat generated is proportional to the square of the current. To manage 312 amps, You would need ridiculously thick copper wire harnesses to prevent them from melting.
And the weight of all that copper would likely push you right over the 450 kilo limit.
Exactly. So the engineering solution is to increase the voltage to lower the current. By jumping to a 72-volt or optimally a 96-volt platform, the required current for 15 kilowatts drops to about 156 amps.
Okay, that's much more manageable.
Having the current dramatically reduces the heat loss and lets us use thinner, cheaper, lighter wiring. This strategic upgrade from 48 to 96 volts is a necessary trade-off to balance electrical efficiency with that hard L7E weight constraint.
Now, despite the regulatory ease compared to a full M1 car, the chief systems engineer still included requirements for energy absorption structures. Why bother with that if the law doesn't strictly mandate it?
That's the difference between merely complying with the law and actually achieving market acceptance. While the regulation relaxes most crash tests, market pressure, the shadow of organizations like Euro NCAP, it all means consumers expect a basic level of protection,
Even in a tiny car.
especially in a tiny car. For a microcar with an extremely short front overhang, we're talking maybe 300 millimeters, finding space for controlled energy absorption is brutal.
So what do you do?
The SR mandates structural designs like replaceable energy-absorbing crash boxes at the very front purely as a proactive measure. It's to ensure occupant survival space, even if the vehicle technically lacks full crumple zones. We design to the spirit of M1 safety, even if we're classified as L7E.
Okay, let's move east to China. You said that their transition to standardized micropassenger vehicles is actually imposing some of the strictest requirements globally.
China's scale and its regulatory evolution make it the most influential market for this whole segment. They are moving so fast to standardize micro-EVs, often imposing rules that are way more detailed and demanding than Europe's.
Let's get into their three major constraints. Starting with the technical conditions, GBT 28382.
Right, so this standard imposes performance minimums, a 30-minute top speed of at least 80 kilometers per hour, and a range of at least 80 kilometers.
So they're ensuring these can be used on more than just city streets.
Exactly. This is China ensuring their LSEVs are capable of higher speed urban ring road use. And the engineering consequence is significant. These requirements necessitate a high-strength steel body structure to handle the dynamic loads.
I see.
And it also forces the inclusion of safety features you'd normally see in passenger cars like ABS and in some high-trim versions of competitors, even airbags. The standard ensures these are not just glorified golf carts.
They're real road-going vehicles.
Small, but real.
Now, for the one constraint that you said dictates our global chemistry choice, the uncompromising battery standard GB 38031-2025. This no fire, no explosion rule.
This is a regulatory game changer. The rule requires that if any single cell in the battery pack enters thermal runaway, a catastrophic overheating event, the fire cannot spread to adjacent cells. Wow. And there can be no external flames or explosion for a full 5 minutes. That 5-minute window is the evacuation time for the occupants.
And you mentioned this virtually mandates lithium iron phosphate, or LFP, chemistry. Why can't the high-density NMC chemistries meet this standard cost-effectively?
Well, NMC chemistries, they offer higher energy density, sure, but they run hotter. And critically, when they fail, they release a significant amount of oxygen.
And oxygen fuels the fire.
Exactly. It makes propagation control extremely difficult and requires extensive, costly fire barriers and complex thermal management systems. LFP, on the other hand, has an inherently superior thermal runaway temperature. It takes longer to fail and it releases way less oxygen.
So for a micro EV where cost and weight are everything.
Engineering the pack to isolate NMC failures to meet that 5-minute rule is often just economically unviable. So the chief systems engineer, using that principle of regulatory harmonization, has to lock in LFP as the global standard for the entire platform because of this one single stringent Chinese requirement.
So what technical features are mandated in the battery pack design to actually achieve this?
The SOR requires robust thermal isolation materials, mica sheets or specialized aerogels between cell groups. But most importantly, it requires a highly engineered directional venting system.
Okay, what does that do?
If gas is released during a thermal event, it must be rapidly and safely channeled outside the vehicle chassis, away from the occupants and the electronics. You have to prevent secondary fires.
Got it. The third constraint is about controlling performance. These dynamic limits, specifically the VCU software lock on acceleration.
This is fascinating. The draft rules require the 0 to 100 km/h acceleration time to be intentionally limited by the software to be no less than 5 seconds.
That seems counterintuitive.
It's not about promoting slow vehicles. It's about controlling torque delivery to prevent accidental damage or loss of control, especially in a segment that's often driven by novice or elderly drivers. It's pure risk mitigation.
But the truly critical active safety mandate here is the pedal misapplication suppression system.
Exactly.
Yeah.
This requires a dedicated piece of software logic in the vehicle control unit. If the vehicle is static or moving really slowly, like when you're parking, and the driver suddenly mashes the accelerator,
Right.
the VCU has to interpret that rapid input as a mistake. The system then actively limits the motor torque, overriding the driver, and it might even initiate light braking. It prevents those runaway collisions in parking lots.
So we've established the core product defined by Europe's weight and power and China's battery and safety rules. How do we address the outliers, the US and Japan?
These markets present binary choices. You either adapt or you exclude them. The U.S. market is defined by the FMVSS 500 low-speed vehicle, or LSV classification. That requires the top speed to be capped at 20 to 25 miles per hour.
Wait, if the LSEV platform can do 90 kilometers an hour, why not just aim for full passenger car compliance in the US?
Because the cost model instantly collapses. Achieving full FMVSS compliance means meeting the same crash standards as a full-size pickup truck. You're talking millions, tens of millions on R&D and testing. You can't build a $7,000 car and then spend $20 million on crash testing alone.
So what's the strategy?
The SOR dictates a strategic retreat. The U.S. vehicle must be tailored only for LSV classification. We electronically limit the speed, add the required safety stuff like reflective tape, and we only target the niche, market-gated communities, college campuses, short-haul delivery. You strategically exclude the U.S. mass market from the global plan.
And Japan's ultra-compact mobility category.
That presents a dimension problem we just can't solve with a global platform. Japan mandates a length under 2,500 millimeters and critically a maximum width under 1,300 millimeters.
And our platform is much wider.
Our global platform is designed for side-by-side seating at 1,490 millimeters wide. That nearly 200 millimeter difference. It's impossible to reconcile without a total structural redesign.
So no simple tweak will work.
No. To get to 1,300 millimeters, you have to adopt a tandem seating arrangement like the Renault Twizy, one behind the other.
Right.
And that fundamentally changes everything. The interior, the steering column, the dynamics. So the SOR has to be realistic and acknowledge that the Japanese market is either excluded entirely or it requires a dedicated bespoke variant, which undermines the whole goal of a single global platform.
And in frugal engineering, exclusion is often the cheapest choice.
It's often the most efficient choice, yes.
The regulatory filter has established our boundaries. So now the SOR turns to the competition. We have to leverage the successful choices of market leaders, Willing, Ami, and Microlino, to justify our own strategic path.
The analysis of these three benchmarks is absolutely essential. They really define the limits of cost, which is Willing, simplicity, which is Ami, and premium quality with Microlino. We have to extract specific engineering inputs from their designs.
Let's start with the cost king, the Willing Hongguang Mini EV. How on earth did they achieve that brutally aggressive cost structure?
Willing's structure relies on a traditional stamped steel monocoque. And this is a technology built on one thing: volume.
Okay.
The unit cost of steel is low, sure, but the initial capital expenditure, the CapEx, for the massive stamping dies and automated welding lines is just enormous. Willing can justify this because their production volumes are over 500,000 units a year.
So for a greenfield project with lower volume targets?
The Willing structure is financially inaccessible. You just can't afford the tools.
But what engineering lessons do we take from them?
Well, first, the sheer efficiency of their supply chain and their willingness to use multiple suppliers for the battery system. They pioneered cell-to-pack integration very early. And second, their mechanical simplicity. A front McPherson strut and a rear 3-link rigid axle. It's cheap, it's robust, and it's totally sufficient for low-speed urban driving.
Does that cheap structure impose any penalties we need to avoid in the SOR?
Oh, absolutely. The cheap monocoque and the high reliance on spot welding without sophisticated dampening contribute significantly to poor NVH noise, vibration, and harshness.
I've heard they can be quite loud.
Willing vehicles are notoriously noisy and feel flimsy at speed. This is a critical takeaway. The SOR platform must aim for better rigidity and NVH to justify a slightly higher price and achieve better crash performance, even if it adds some complexity. That leads us away from a purely stamped monocoque.
Next, the Citroën Ami. This vehicle is the definitive masterclass in that frugal engineering design philosophy.
The AMI demonstrates how to minimize investment, not just parts cost. The SOR heavily incorporates two key innovations from the AMI: symmetrical design and the space frame plastic panel concept.
Let's talk about the symmetry. Using identical molds for the left and right doors means one door has to be rear hinged, a suicide door, and the other is front hinged. Is that tooling cost saving really worth that functional compromise?
That is the crucial trade-off. From a user standpoint, yeah, the dual-hinge door system can be a bit clunky.
Bit weird, yeah.
But the engineering cost reduction is immense. By cutting the number of unique large tooling molds down, you might cut your tooling capex by $5 to $10 million in the initial setup. For a greenfield team, that capital preservation is non-negotiable. The SOR dictates that the aesthetic penalty and the minor inconvenience are acceptable trade-offs for that massive tooling cost saving and simplified inventory.
And structurally, the AMI space frame approach is key for a low-volume start.
Yes. Unlike Willing's massive investment in stamping, the AMI uses a tubed steel space frame cage with non-load-bearing plastic panels attached to the outside.
Right.
This dramatically lowers the initial capex and allows for a much smaller, specialized factory footprint. Plus, in the fleet or rental market, those plastic panels are cheap and easy to swap out, which minimizes repair costs.
The simplicity extends right into the cockpit with the bring your own device or BYOD strategy. What functions are we sacrificing by eliminating the integrated infotainment system?
Well, we sacrifice embedded navigation, sophisticated vehicle diagnostics, complex audio tuning, high-res camera displays. A dedicated IVI system requires an expensive CPU, software licensing, continuous development. By using BYOD, you offload all of that cost to the user's phone.
But does that compromise key safety features like the tire pressure monitoring system?
No, the system retains essential mandatory features. The basic vehicle status speed, state of charge, warning lights, raw TPMS data is all displayed on a minimal, low-cost LCD screen.
Okay, so the basics are there.
The basics are there, but the advanced user interface features, like a graphical display of charging time, that gets pushed to a dedicated app on the user's smartphone. You're saving on expensive hardware while maintaining regulatory compliance.
Finally, the Microlino 2.0, representing the premium LSEV path. What lesson did the SOR take from their structural evolution?
The Microlino demonstrates the cost of quality. They moved from a simple space frame in their first version to a premium steel and aluminum hybrid monocoque in version 2.0.
And why did they do that?
That shift was driven by customer expectations around NVH. A traditional non-bonded space frame often transmits road noise and vibration pretty harshly. By investing in the stiffer hybrid monocoque, they dramatically improved the perceived quality and safety, which let them justify their higher price point of over 15,000 euros.
So the key learning is that while the Willing structure is too cheap and noisy, the Microlino structure proves the need for enhanced rigidity, even in a small vehicle.
Exactly. The benchmarking confirms that a basic tubular space frame isn't quite good enough for the modern consumer or for managing collision forces effectively. Right. We need something that leverages the low capex of the space frame, but integrates advanced stiffness technologies like structural adhesives to mimic the rigidity of a premium monocoque.
We have our constraints and our competitive intelligence. Now we build the car using the specific technical requirements from the Vehicle Technical Specification, the VTS. Let's start with the Goldilocks dimensions.
The dimensions are all carefully chosen to maximize urban utility while sticking to that L70 width limit. The strategic target length is 2,950 to 3,050 millimeters. Crucially, controlled right around 3 meters.
And the primary purpose of that length isn't aerodynamics, but something else.
It's all about parking flexibility.
Tell us more about this cross-parking feature.
In many big European and Asian cities, parallel parking spaces are sized for cars that are, 4.5 to 5 meters long. If our vehicle is under 3 meters long, local rules often allow it to be parked perpendicular to the curb.
Ah, so you can nose in.
You can nose right in. It's called vertical or cross parking. This is an enormous urban utility feature and a massive selling point.
The width is 1,490 millimeters, just shy of the 1,500 millimeter L70 maximum. Why push it so wide?
Well, we chose a side-by-side seating layout for 4 passengers, a modular 2+2. And to comfortably accommodate the 95th percentile male shoulder width without feeling totally cramped, you need every millimeter.
But that immediately disqualifies the ultra-narrow Japanese market.
It does. But it maximizes the utility and comfort for the core EU and Chinese markets, which are used to side-by-side cars.
And the wheelbase is 2,100 millimeters. That's pretty tight.
It is short, and it's driven entirely by maneuverability. The SOR mandates a maximum turning radius of under 4.2 meters. A short wheelbase is the engineering lever we use to achieve that tight circle. It's essential for narrow city streets.
And of course, the curb weight, excluding the battery, has to stay under 450 kilos.
The non-negotiable hard line. Hitting this weight target requires extensive use of advanced materials, high-strength steel for the critical cage areas, and engineered plastics for all the non-structural panels and interior trim. Weight is tracked on every single component.
Okay, let's move to the foundational structure.
No.
The chassis architecture. Given the high-volume success of Willings monocoque and the low-cost simplicity of AMI's space frame, why did the chief systems engineer choose an improved tubular space frame for this SOR?
For a greenfield project targeting lower initial volumes, the cost of stamping tools for a monocoque is just prohibitive.
Right.
So we need the low capex of the tubular space frame, but we have to solve the NVH and rigidity problems of the basic AMI design. So the improved structure uses higher strength, precision-bent square steel tubes for the occupant cage.
And how do we tackle NVH and rigidity without adding massive amounts of steel?
This is where the structural adhesive strategy comes in. We're minimizing traditional spot welding, which creates localized stress points and is poor at acoustic damping, and increasing the use of structural adhesives throughout the body in white.
And what does the adhesive do?
Adhesives distribute stress over a wider area, creating a stiffer, more homogeneous bond. This dramatically increases the body's torsional rigidity, and crucially, it improves NVH performance by dampening high-frequency road vibrations. It makes the car feel more robust, more premium.
What about the floor structure that houses the battery?
That's the second critical structural component, the skateboard double floor structure. This isn't just a plate, it's a fully engineered enclosure integrated into the frame.
And it serves two functions.
Right, to ensure a low center of gravity for stability, and more importantly, to act as a crucial structural barrier for side impacts. By making the floor and battery tray integral to the structure, you gain vital side impact protection, which helps satisfy that no-fire mandate.
Moving to the power source, we established that the 96-volt nominal voltage platform is the strategic sweet spot. It avoids the complexity of 300-volt systems. Can we quantify the savings by stopping at 96 volts?
Sure. The jump over 60 volts DC technically puts us in the high voltage category, so it requires some safety measures. But stopping at 96 volts prevents the need for the extreme isolation and component cost mandated by systems over 100 volts, and especially over 300.
So what specific expensive components do we get to avoid at 96 volts?
We avoid high-cost certified HV connectors, which can cost $50 to $100 or more per pair compared to maybe $5 or $10 for a low-voltage one. We also minimize the complexity of insulation monitoring modules, specialized high-voltage fuses, and contactors.
I see.
And it even simplifies the factory environment. Assembly workers require less specialized high-voltage training and tooling. It's just the perfect balance of efficiency and cost for a 15-kilowatt application.
What are the specific motor requirements for this 96-volt platform?
The SOR specifies a permanent magnet synchronous motor, a PMSM, for its efficiency and torque density. While we need about 20-25 kilowatts of peak power for rapid acceleration and safety margins.
Like merging onto a busy road.
Exactly. But the software has to limit the continuous rated power to the L70 maximum of 15 kilowatts. We're targeting a peak torque of 90-110 newton meters, which is plenty to move a 450-kilo vehicle quickly in a city.
And the cost-saving choice in thermal management is air cooling.
Yes. For a 15-kilowatt motor, a liquid cooling system, a pump, radiator, coolant lines, it all adds significant cost, weight, and potential points of failure. So the entire system is mandated to be air-cooled. The engineering challenge then is just designing highly optimized cooling fins and air ducts to make sure it doesn't overheat.
The layout is rear-wheel drive, RR. That seems less common for modern city cars, which are usually front-wheel drive.
The choice is a direct safety and packaging decision, dictated by the car's tiny dimensions. In a car with an extremely short front overhang, putting the heavy motor and drive unit up there consumes valuable space that you need for frontal energy absorption.
Ah, for the crash boxes.
Exactly. By moving the motor to the rear, the RR layout, we free up the entire short front structure for dedicated replaceable crash structures. It significantly enhances frontal passive safety, which is paramount in a vehicle this small.
Now, the energy storage system, the ESS, we established that LFP chemistry is non-negotiable because of that Chinese no fire, no explosion standard.
Precisely. LFP's inherent stability dictates the chemistry choice for the entire globe, ensuring we satisfy that superset regulation. And it's a critical safety feature that also doubles as a cost advantage, since LFP is cheaper per kilowatt hour than NMC.
And the packaging has to utilize the inherent safety of LFP, module-free or cell-to-pack, CTP.
CTP leverages LFP's ruggedness by integrating the cells directly into the pack shell, removing that intermediate module structure. This gives you two huge advantages for frugal engineering.
Okay, what other?
First, it boosts volume utilization by 15–20%, so you can pack more kilowatt hours into a smaller space. And second, it reduces the bill of materials by removing module components, which typically shaves about 10% off the battery hardware cost.
What are the capacity and charging targets?
We need modularity for pricing. The SOR mandates a standard version, around 9 to 10 kilowatt-hours for a 100-kilometer range, and a long-range version, maybe 15–17 kilowatt-hours, and for around 170 kilometers.
And charging?
It has to be dual mode. It needs to support the standard public Type 2 interface. But critically, it has to retain an internal telescopic household plug. This charge anywhere convenience, inspired by the AMI, is key for users who live in apartments without dedicated EV chargers.
The structural foundation is set. Now we turn to the nervous system, the electronic and electrical, or EE, architecture. How does cost efficiency dictate the design of the vehicle's brain?
By ruthless segmentation and simplification. We use a standardized distributed architecture with high-speed critical systems, the VCU, the BMS. They communicate over the robust CAN bus. But for all the non-real-time peripherals, lights, windows, wipers, we use the simpler, cheaper, and lower bandwidth LIN bus. This hybrid topology saves substantial weight and cost on the wiring harness.
And the cost-saving measure we discussed earlier, the HMI strategy, complete elimination of the complex central screen.
We reduce the HMI hardware to the bare regulatory minimum. A simple, low-resolution 5 to 7-inch LCD cluster for mandatory data. The BYOD strategy offloads all the infotainment complexity to the user's phone.
Saving hundreds of dollars per unit.
Easily. You remove the need for expensive screens, navigation hardware, powerful CPUs. Even the audio system is just a basic Bluetooth amplifier.
I want to focus on cybersecurity. Even for a simple L7E quadricycle, the SOR mandates compliance with UN R155 and R156. That seems like high-end complexity that undermines frugal engineering. Why is it unavoidable?
It's unavoidable if we want to sell the vehicle in the EU and if we want the capability to do over-the-air software updates. UN R155 and R156 compliance is mandatory for new vehicle types. And it's not just about adding a hardware security module to the VCU.
What is the real cost and complexity buried in these regulations?
The real cost is in the process management. Compliance requires the OEM to maintain an auditable system that tracks every line of code, manages vulnerability reports, monitors the security of the entire supply chain.
So it's a huge administrative overhead.
A huge overhead. Yeah. For R156, every single software update must be logged, verified, traceable. This demands specialized staffing, continuous monitoring, rigorous documentation. It is a necessary tax for operating in regulated markets, no matter how simple the car is.
Let's pivot back to safety engineering, our frontline defense. We can't rely on mass, so the focus is on active and structural protection.
For active safety, the SOR requires more than the regulatory minimum. While L7E just mandates a combined braking system, we strongly specify ABS for stability and mandatory AVAS below 30 kilometers an hour to protect pedestrians.
And that critical pedal misuse suppression system we derive from the Chinese standards. How does the VCU actually implement that torque limit?
It's an algorithm based on comparative analysis. The VCU monitors multiple inputs: how fast the driver pressed the pedal, the vehicle speed, the gear position.
Okay.
If the VCU detects a very high rate of pedal input that's inconsistent with the vehicle's state-like mashing the throttle while stationary, it just bypasses the driver's demand. It limits the torque to a safe crawling level. It's a purely software-based feature that drastically reduces low-speed accident risk.
Given the minimal front overhang, how do you physically manage frontal passive safety?
We use the concept of sacrificial structures. The SOR mandates replaceable steel or aluminum crash boxes mounted to the front of the space frame.
Yeah.
These are designed to crush and absorb energy during low-speed impacts.
So they protect the main occupant cage.
Exactly. And they're designed to be cheap and easy to replace, which minimizes repair costs.
And what about the battery?
Battery protection during a side impact is crucial. The design requires high-strength sill beams reinforced components running under the doors, surrounding the underfloor battery pack. These beams have to withstand specific impact tests to prevent the pack from deforming.
And the required use of pre-tensioner seatbelts. That sounds like a costly component for a microcar.
It is, but it's a non-negotiable life-saving feature.
Why?
Because the vehicle has extremely limited frontal crush distance. The speed at which the restraint system secures the occupant is paramount. Pretensioners rapidly cinch the occupant back into the seat just milliseconds before impact, minimizing forward travel. That fraction of a second is vital for survival in a microcar.
Let's move to the manufacturing side. How do we achieve those brutal cost targets? The SRR outlines a radical approach, the microfactory concept.
The microfactory is the industrial expression of frugal engineering. It attacks the traditional automotive four processes, stamping, welding, painting, and final assembly, by strategically eliminating the most capital-intensive steps.
Which three processes are being effectively eliminated or drastically simplified?
We essentially eliminate stamping and painting entirely.
So you just skip painting altogether?
We do. Stamping is gone because we use injection-molded plastic panels that arrive pre-colored from the supplier. This completely avoids the massive investment in stamping tools and, crucially, removes the entire capital-intensive painting line.
Which can be a huge part of a factory.
It can be half the factory's footprint. We only retain the e-coating stage to prevent rust on the steel space frame. Welding is also drastically simplified. Instead of massive spot welding lines, we use automated bending and robot welding stations dedicated only to the structural cage.
That dramatically reduces the factory footprint and the initial capital outlay. What about the supply chain strategy?
The supply chain has to reflect the frugal mandate. For LFP cells, which are up to 30% of the B, we prioritize sourcing from specialized Tier 2 Chinese suppliers.
Wait, using a Tier 2 supplier introduces more risk, doesn't it, in terms of quality and warranty?
It's a calculated risk management strategy. We prioritize suppliers who have scaled up successfully in the low-speed or industrial sectors. They often offer a 10–15% cost advantage over the big Tier 1s.
And you mitigate the risk how?
Through rigorous independent testing and by requiring dual sourcing agreements. We accept a slightly higher warranty risk margin in exchange for immediate cost competitiveness. It's a key decision for the chief engineer.
I see.
And it's the same for the motor and control units. We source from the industrial sector to avoid the prohibitive upfront engineering fees from traditional auto suppliers.
And the final genius efficiency measure, the tires.
Low rolling resistance, narrow tires. A 4L 570 R12 setup. It is the cheapest, simplest, and lightest method available to marginally boost energy efficiency and extend range, with zero added cost or complexity to the expensive powertrain.
Let's look at the financials. What is the target BOM cost for this whole effort, and how is profit actually generated?
The aggressive target for the bill of materials cost for the high-spec L7E model is somewhere between $6,000 and $7,000 USD. And as we noted, the battery is the single largest component, around $1,500 to $1,800 of that.
So if the car retails for, say, $10,000, the hardware margin is paper-thin after you account for everything else. How does a company truly profit?
Profitability relies on two critical non-hardware elements. First, carbon credit trading, especially in China, which effectively pays EV manufacturers for every zero-emission vehicle they sell.
Okay.
And second, high-margin personalized aftermarket accessories. Following the AMI model, the base car is a thin-margin product, but custom decals, colored trim kits, unique storage solutions, these can command 50% to 80% margins and form a substantial part of the total profit.
Finally, the timeline. For a greenfield project, a 24-month development cycle seems extremely aggressive.
It is a high-pressure, compressed schedule. M0 is the start of the project. M24 is the start of production. The key to success is the prototype verification phase from month 13 to 18. During this time, we have to subject the vehicle to 15,000 kilometers of accelerated durability testing.
Which simulates a much longer lifespan.
It simulates the harsh stresses equivalent to 150,000 kilometers of real-world customer use, ensuring the low-cost components don't fail prematurely. The final months are just dedicated to regulatory homologation and ramping up pilot production. The entire exercise of defining this engineering requirement specification really demonstrates that the success of a micro-EV platform, it doesn't lie in technology stacking. It lies in the precise and sometimes brutal definition of the boundary of enough.
Enough, yeah.
You have to deliver sufficient performance, robustness, and safety to meet the regulatory minimums, coupled with the absolute minimal cost necessary to be commercially viable. The complexity of global regulations, especially China's stringent battery standards and the EU's strategic L7E weight limit, has to be absorbed entirely by the initial architecture. That's the only way to get maximum market scope at minimum industrial cost. That is the ultimate test of frugal engineering.
It truly is a masterful lesson in designing backwards from the most severe constraints, where a single regulation half a world away dictates the global choice of battery chemistry. That focus on LFP just defines its entire market segment. So here's the final provocative thought for you to consider. The entire engineering blueprint we've discussed, the 96-volt system, the cell-to-pack strategy, the thermal management, it is all fundamentally predicated on the inherent stability and cost advantage of lithium iron phosphate, which is necessitated by that no fire, no explosion rule. What happens to the global LSEV market if a technological breakthrough in NMC thermal stability suddenly makes it cost competitive with LFP, offering higher energy density at the same safety profile? Would the current focus on the 96-volt architecture and CTP design become immediately obsolete, forcing engineers to switch back to higher voltage systems to fully utilize that lighter, denser chemistry? Or is the inherent simplicity, the ruggedness, and the stable supply chain of LFP still the ultimate expression of frugal engineering, regardless of what its competitors can do? That core trade-off between today's efficiency and tomorrow's technology is what every chief systems engineer faces daily in this volatile, fascinating market.